Hey AP Chemistry, this is Miss Gray.
And this is Mrs. Uy.
And we're going to work on deviations from ideal gases. Remember the ideal gas law?
Yeah.
PIV-NERT?
PIV-NERT.
Okay, well, we're going to tell you when PIV-NERT doesn't work very well.
Oh, okay.
Okay, deviations
All right.
from ideal gas.
Okay.
So when we talked about ideal gas laws, we also talked about the kinetic molecular theory and explaining why things happen for a theory, and these assumptions we're going to go quickly through. First of all, we said that ideal gases, we assume that the particles are so small that we can ignore their volume.
Yeah.
So in PIV-NERT, this piece right here, the volume piece, would only describe the volume of the container, but not the volume of the gas itself.
The gas itself.
Right?
Okay.
So that's one of the assumptions that has to be true for PIV-NERT to work. Another one is that particles are in constant motion, they don't stop.
Yeah.
And that their collisions cause pressure.
Yeah. So when they're moving, they create pressure.
Yeah. And then another assumption is that the particles do not affect each other. They don't attract and they don't repel. But what we know in reality is that some particles have polar molecules where there's a positive charge and a negative charge on one side or the other. And what that means is that the particles actually do affect each other.
Yeah.
For PIV-NERT to work, then they have to not push or pull.
Okay.
Right? So is there really a gas that doesn't do that? No.
No.
Not perfectly well.
Yeah.
Then we also would say the average kinetic energy is proportional to the Kelvin temperature. And what we learned in class yesterday is that this usually works on average, but there's always fluctuations.
Yeah.
Right? And then also to describe temperature, we would use the kinetic energy formula from physics.
Yeah.
Do you remember this one?
Oh,
right?
yes.
1/2 mv squared.
mv squared.
Right. It's been a long time since we got to do physics.
Oh gosh, I don't know. I don't want to tell because the kids will know.
Then they'll know how old we are. They already have an idea, I'm afraid.
Yeah.
At least for my age. Deviations from ideal behavior would mean that in this instance, ideal gases are assumed to occupy no space and have no attractions, but real gases have definite volumes. Right. And they do attract one another.
Yes.
So engineers and chemists who work with gases at high pressures could not use the ideal gas law as it is. Because once you have a high pressure, you squish the particles closer together.
Yeah.
And their attractions for one another become more important, right? If they have the charges, then under high pressure, they'll stick together more.
Yes.
Right? And then another situation would be at very low temperature, or sometimes at very high temperatures. This becomes important. Okay, so here's what we do to adjust for those conditions.
Okay.
Remember PIV-NERT, of course?
Yeah, PIV-NRT.
Well, this guy van der Waals, you know, another dead
white
white guy.
Another dude.
One of those scientists, he said, here's a way to adjust for the volume of the molecule, and here's a way to adjust for the attraction the molecules have.
Okay.
So we use these two terms in what we call the van der Waals equation. So we can adjust for situations when the gas is not ideal.
Yeah.
So A and B are called van der Waals constants.
Okay.
For every gas, this letter B and this letter A would represent a different number for each individual type of gas.
Okay.
Where B describes the volume for that gas.
Okay.
Okay, so imagine the hydrogen molecule is very tiny.
Yeah.
Butane molecules are gases in your candle lighters. Look how big that is.
Yes, it's
and then we put hydrogens.
Large molecule.
Yeah. All of my students have studied how to name organic compounds, so they had better know how to draw this.
Oh.
Butane.
Wow.
Right. That's a lot bigger than hydrogen, which is this. Yeah. So we would have a bigger correcting factor for butane than for hydrogen. Does that make sense?
Yes.
Okay. Now let's talk about the A factor. This one
the molecular attraction?
Yeah, corrects for molecular attraction. So if we have a particle like water, where we have a definite side that's negative and a side that is positive, then this is a polar molecule. we have to adjust for this particle. Let's compare to a nonpolar, like that hydrogen molecule. Neither side is more positive than the other. And so we'd have a very small factor for hydrogen here.
Compared to water.
Compared to water.
Okay.
Right. That doesn't mean this is zero. It just means it's very small.
Very small.
Yeah. Because there's other forces that after Christmas we're going to talk about those. So let's see, what do we do with this? Well, here's an example of the A's and the B's. Hydrogen's way down here. The one that has the least mess. Oops. Whoa, that's not hydrogen. That one's hydrogen. I can't even draw my arrows right. It's the end of the day. We're tired.
I know.
Okay, so look. Helium, neon, argon, krypton, and xenon. What do you think of that? Those are all noble gases.
Yeah, noble gases.
Right, so they're going to have pretty small
corrections. Yeah.
Yep, and then hydrogen, of course, has a small correction. And then it gets bigger and bigger. And here's a molecule that has polar bonds, but a non-polar geometry.
Yeah.
But carbon tetrachloride is much larger and bulkier than methane gas, for instance. And so that halocarbon would have to have more corrections than methane. The regular alkane.
Okay.
I have to see if my students remember these words. Halocarbons and alkanes.
I bet they're going to remember that.
I bet so. It wasn't that long ago, only fall break.
Okay.
Okay, so we need this table. Do you have that table?
Yes, I think I do.
Okay, we're going to use it. Here's what we can do for PivNert. Look, here's our pressure and our volume. PV equals nRT.
nRT.
Right?
Yes.
Only we've corrected for the pressure using the A factor.
Yeah.
We've corrected for the volume.
The volume factor using the B.
Yeah, using the volume of each gas.
Okay.
So that means the volume of the container minus whatever space the molecules themselves take up.
Gotcha. Okay.
And then N still stands for moles. How many moles of that gas do we have? That makes sense. We'd have to have that in there.
Yes.
Okay, so now let's see what to do with this. Oh, we already said this. The more massive particles have larger volumes.
The larger volumes and greater intermolecular attractive force.
Right. So let's do an example finally.
Yay! Problem!
Calculate the pressure exerted by 0.5 moles of chlorine in a 1 liter container at 25 degrees Celsius. So normally, if I tell you to calculate the pressure, you
PV and RT?
Hey, no problem. We can do it. Except now.
This is not.
Yeah, this is not normal. So chlorine has these adjustments to make. A was the adjustment for the attraction of the particles.
Yep, that's 6.49.
Okay, and then B was the adjustment for volume.
Yes, in the table it says 0.0562.
Okay, now we got to find that equation where we rearranged this one. So it's P plus
N squared A.
All right.
Over V squared.
All right.
Times.
They're going to make this math hard today.
Right.
Oh, times.
Yeah.
All right. P times V, not
V minus NB.
Okay.
Which is equal to nRT.
Oh, nRT.
Yep.
Okay. Sounds like our normal PivNert.
Yeah.
Almost. So we have all the information we need. Look, we have moles.
All right.
We have our volume.
And we have temperature.
We're finding pressure. We know what R is. It's still 0.0821.
Yeah.
So let's just put in our numbers. We'll do pressure is equal, solving this for pressure. Yeah, we can do this. Divide both sides by this term and then subtract the things. Okay. So nRT divided by V minus NB, and then subtract N squared times A over V squared. Does that look like it'll work?
I think
to
so.
get P by itself?
Yep.
Okay. Time to put numbers in.
So N
is 0.5 moles. And we're going to multiply by R, 0.08206. And that's liters times atmospheres over moles times Kelvin. And then T is, can you change that to kelvins? Add 273 plus 25. Cuties.
273 plus
25.
25. Oops, it's not even on.
Oh.
273 plus 25. 298.
Okay. 298 kelvins. You already knew that.
Yeah.
Without a calculator.
Yeah.
Yeah. Okay, now, on the volume, we have 1 liter. 1 liter minus N, so 0.5. Times B. And our B in this case was
0.0562
liters per mole.
per mole.
Oh, I didn't put my moles in here. Let's
So
check
cancel
our
out
units.
moles.
Yeah, moles goes away. And then
liters.
liters time, liters is not gone yet. Oh, up here.
Up here.
Liters and liters. Kelvins and kelvins.
Kelvins.
Moles and moles. And then,
So we have 18.
oh wait, this liters because we subtracted, right? So we'll have liters all gone on the bottom. And then atmospheres is all that's left since we're trying to find pressure.
Yeah, which
that's
is
good.
The unit for pressure.
Okay, so far I've only written this first piece. We got to do this piece.
Oh, yeah.
Minus, I better change colors because I'm going to go off the screen. N squared, so 0.5 squared times A.
A is 6.49.
Okay. And then divide by the volume squared. 1 liter squared. I can do that in my head. Oh, I didn't put any units here though. So I have moles squared and
ATM.
Oh, look, this is liter squared over mole squared. So all those units went away.
Yeah.
Nice.
Nice. So we end up getting ATM.
Good. Now, where am I going to put our answer?
Just
right
make an
here.
arrow.
Oh,
yeah,
we'll
on top.
Okay.
Your kids is good in following you, Ms. Gray.
That's right. It's time to run the calculator. I'm glad this is your job. Okay, so let's do 0.5
0.5 times
0.08
0.08
206
206
times 298.
298.
Okay, and then we're going to divide by the quantity of something. So use parentheses, or that works.
Okay.
So do divided by parentheses. Yeah, right there. 1 minus 0.5 times 0.0562.
All right.
Okay, close your parentheses and hit enter. And what do we have for this term?
It's 12.58. How many sig fig are we going to use?
That's good for now.
All right.
We'll just keep the rest in our calculator.
All right.
So that's our first term. Now let's do the second term. We have 0.5 squared times 6.49.
Times 6.49.
Okay. What do we get? And then divided by 1 squared. So we don't need to do that in the calculator.
1.6225.
Okay, subtract those two.
All right. 12.58 minus 1.6225. That should give you 10.9575.
Okay, and that was
That's
in
80.
atmospheres.
Yeah.
So let's look at sig figs. 4, 3, 4. Looks like 3 sig figs. 1, 2, 3. So we get to call this 11.0 ATMs. And I better put a box around that so we can see my answer. It's messy.
Knows where is the final answer?
Right. So we would normally just use Pivner.
Okay.
But in situations where the gas is under high pressure or at extreme temperatures, we'd have to make these adjustments using the van der Waals equation. Unless we have a really weird gas. The gas that's closest to ideal was helium.
Yeah.
Yeah. And helium's a fun gas.
It is.
We should bring in helium balloons. And we'll do a podcast
My
with squeaky
kids told me
voices.
something about the helium gas that they learned from you. So.
Oh, okay.
And they challenged me to try it. And it's like, no way.
I think they're making stuff up. All right, our podcast is done. Bye, guys. Have a good day. All right.
Oh, I thought there's one more slide. Did it stop?
I think it's done. It better be done. Yeah, that's all.